Yes.
Hello.
Good. All right. So we have 2 weeks left. I think we will. So we have one last little section we have to do that you guys need for midterm 3. So I think we'll finish that. We have to do the QR decomposition. And then we have one more chapter on inner product spaces, but that one is not going to be on your midterm 3. I think maybe we'll just finish the section you need for midterm 3, and then maybe we'll do a little bit of review for midterm 3 and maybe do the inner product spaces next time. How's that sound? And so we kind of get the midterm 3 out of the way first.
Sounds good.
All right, so but the review, I mean, we're pretty much finished all of the chapters. Well, the section that we need to do from chapter 6, right? We're not going to do all of them. So we're just doing 6.1 through 6.4. Right? But last time we did 6.4, right? Kind of little review, right? So we're talking about orthogonality and orthogonal bases, right? So kind of the review, like the set of vectors is called orthogonal if basically they're all mutually orthogonal, right? So for sets of two distinct vectors, the dot products are 0. And also we showed that if the set is orthogonal, it necessarily is going to be linearly independent, right? So if you find an orthogonal set with p vectors in a subspace of dimension p, then it's automatically also going to be a basis because it's automatically linearly independent, right? And then orthonormal bases, I mean, they're also orthogonal bases, but they have an extra condition that not only my vectors are orthogonal to one another, but also they're all unit vectors. So kind of the length of the vectors equals to 1, right? Or their dot products equal to 1. Because remember, those dot products are always positive, right? So if the square equals to 1, then it's equals to 1. So then we also did kind of like decomposition of our vector y. So if I have some subspace W with orthogonal basis for that subspace, right? Then remember when we had just linearly independent basis vectors, like we had to do, if I wanted to find the weights for my basis vectors for my vector y, I had to solve a linear system. But if I have an orthogonal basis, it's a lot easier because I have a nice little formula for computing my weights. I don't have to solve linear system anymore. I can just use it, I can just do it using dot products, right? So my decomposition of y and the basis vectors u, right? My weights are just given by y dot u dot u in the denominator, right? So I'm taking projections of vector y on all of those basis vectors to get my weights, right? And then like the big part of last time, what we did is we talked about kind of like, again, those projections, and we did the Gram-Schmidt process. With projections, I mean, all it says is if I have a vector y in some general vector space, and the vector space has a subspace W. So W is not all of V, right? It's some subspace of V, right? And for that W, I have an orthogonal basis. So my U1 through UP is an orthogonal basis for the subspace W, right? So Y is not necessarily in W, right? But what I can do is I can always decompose my vector Y into the sum of two vectors, where one vector is in W, and then another vector is going to be an orthogonal complement to W. And so my vector that's in W, I'm calling the orthogonal projection of Y onto W. And graphically, that just looks like, if I have a vector Y here, and this is my subspace W, my orthogonal projection is basically kind of, you can think of it as like the shadow that Y casts on W, right? But graphically, just basically going at the right angle to W, and this is going to be my Y hat, and it's my orthogonal projection onto W, right? And then the second vector, I mean, when you compute this, you just take the difference between your original vector and Y hat once you get Y hat. But the second vector is going to be the component of Y orthogonal to W, right? So, I mean, we're placing vectors in the origin, but I mean, this vector here, my Z, I mean, if I place it over here, it would just complete the side of this right angle triangle here, right? So I'm kind of decomposing this vector into something that's in W and something that's orthogonal to W. Right? And then to compute your projection of y onto W, I mean, we have, it's basically the same formula as we have over here, right? You can think of it as kind of, if I have several vectors spanning W, so I have a basis of P vectors, I'm basically summing up projections on those one-dimensional subspaces spanned by those vectors. Or if I'm taking the sum, it's basically full projection onto the whole subspace W. Right, so you can always kind of use this formula when you do this. And to compute z, I mean, you already know y you're given to you. If you compute y hat, you can easily compute z by just kind of subtracting y hat from y. Right, and this would be my orthogonal component of y. Right. Yeah, and then also in applications, like when do you use this? I mean, sometimes you want to find, like, what is that best approximation theorem to y by elements in W, right? So maybe, I have some vector y, but I can only use vectors in W to kind of do my computations. So how do I approximate y by only using vectors in W? And your best approximation is going to be that projection y hat. Right, so y hat is kind of like the best approximation to y if I'm only living like in the subspace W, right? So you just compute it the same way. And also kind of types of questions when you want to find the distance between a vector and the subspace, right? Like the distance between a vector and a subspace would basically be the shortest distance from the vector y to my subspace W, which happens to be the length of this vector here, which is the length of that y minus y hat. Right? So distance between vector to the subspace is kind of length of the vector y minus its projection onto W. And all that's like all of the formulas you need to do the problems for this. And the last thing we did last time was, kind of talked about if I'm putting those orthogonal bases into a matrix, right? And I mean, it's not necessarily going to be a square matrix, right? It would be like n by p, right? Because if, if this spans subspace of dimension p, right? But my kind of larger subspace is v with dimension n, right? Those vectors would be like in the Rn, right? But I have p of them. So if I put them as columns in the matrix U, it's going to be an n by p matrix, right? I have p columns or n rows. Now, but it doesn't have to be square, right? We showed in the theorem that if my columns are orthogonal, then my ut times u is going to be identity matrix. Now, and then if they're orthonormal, well, actually, this is also going to be no mind. So if they're orthonormal, not only that, I can actually rewrite my formula for the projection. Remember, orthonormal means that they have length 1, all of those vectors. Right? So my ut times u will be identity matrix, but we also kind of rewrote the formula for the projection y onto subspace W with u times u transpose. Right? I mean, it's just literally the rewriting of the formula here, provided my dot products are all equal to 1. But I mean, in a lot of cases, I mean, you're dealing with square matrices, and if your matrix is square, so basically you're taking the orthonormal basis for all of Rn, right? So this all of Rn, orthonormal basis, and you put this as columns in your matrix U. I mean, then your U transpose times U and U times U transpose are going to be equal to the identity matrix. And it makes sense because projection of y onto W, if W is the entire V, then, I mean, it's just going to be the same as y. I'm basically projecting y and v on v itself. So it will be an identity, right? But in those cases, if I put my orthonormal basis in the matrix, right, then basically I end up with a matrix where my transpose of the matrix equals to the inverse of the matrix, which is very nice, right? Because remember, if I don't have orthonormal columns in my matrix and I want to find the inverse, I have to do this like row elimination, and it's like a little bit tedious. But in this case, it's actually really easy to find U inverse because it just equals to U transpose, right? But you do need to have a square matrix, so you need to have a basis for all of V, and it has to be orthonormal, right? And then the big theorem of that chapter was the Gram-Schmidt process, right? Because those orthonormal bases are so useful. I mean, how do we construct them, right? Because in general, I may only know like some basis for subspace W. So if I know any basis, right, it doesn't have to be orthogonal. It just has to be, you know, linearly independent set that spans my subspace W, right? So my X1 through XP is any basis. But the Gram-Schmidt process basically gives us a recipe for constructing an orthogonal basis from any other basis for W, right? And basically you kind of go generate vector by vector. Like the first vector, you can take the same as the first vector here, right? Then the second vector, you basically take in the second vector and your basis, X, and you're going to subtract from that X the projection of X onto the previous vector. So you're basically only taking the part of X2 that is orthogonal to X1 to become your V2. Now, once you get that, you go to the next one, V3. You take the next vector X3 from your set, and then you just subtract the component of X3 that lies in the span of the previous two vectors, V1 and V2. So again, you basically, for V3, you're taking the component of X3 that is orthogonal to my previous two vectors. So I'm basically generating one by one those new vectors in my basis that by construction are all going to be orthogonal, right? Because each new one is orthogonal to all of the previous ones. So in this way, my set is going to be orthogonal. And also not only that, if I'm doing it in this way, I can even like stop at any time and I will have like span of X1, X2, X3 is the same as span of V1, V2, V3. Right? If I go one more, span of X1 through X4 is the same as span as V3 through V4. You can do that all the way to the end, VP. That makes sense? All right, we'll get some, we're gonna use the consequence of that example. So we did some examples last time, right? So I had three vectors, right, that form a basis for some subspace W, right, of R4, right, because I have four elements, but I have three vectors, so it's subspace of dimension 3 in the space of dimension 4. And if I want to construct the orthogonal basis, right, I'm starting with X1, V1 is X1, right? And then to construct the second one, I'm taking my X2 and subtracting projection of X2 onto my X1, right? So it would be X2, X2.V1, V1.V1, V1. And then you're just computing this, right? So my V1 and V2 will be orthogonal. And then I have three vectors, right? So I have to do V3 also. But before you do V3, remember, this is your basis, right? So all of the vectors that you're expressing, you know, in terms of weights multiplied by those basis vectors, I mean, everything is up to kind of multiplicative constant. So when you do those problems, so here I computed my V2, right? So this vector is orthogonal to V1 or X1. But I have all of these fractions here, and I'm going to still have to do some computation. There's nothing wrong with just rescaling it a little bit, right? I can always multiply this by some constant, right? Because I mean, all of my basis vectors are just up to multiplicative constant, right? I'm taking spans, right? And it doesn't change orthogonality at all either, right? Because multiplication by constant, if my dot product is 0, then, I mean, it's just still going to be constant times 0. So it's helpful to rescale it at this step, right? So I don't have to deal with those ugly denominators. And so I can just like multiply V2 by 4 and rescale it into -3, 1, 1, 1. Right? You don't have to, but I mean, it does help kind of when you continue doing your calculations, because if you have a bunch of denominators, you have to then add and subtract things and bring things to common denominators. It just becomes harder, right? And much easier to make mistakes. So kind of try to rescale your stuff at every step to make your vector look kind of a lot easier to deal with. It's the next step, right? Because you keep going like step by step to generate each new vector. All right. So now I have my V1, which is the same as X1. I have V2, and then to get my V3, right? Kind of same procedure, except now I am projecting on two-dimensional subspace, right? So to construct my third vector, I'm taking X3, the third vector on a given basis, and subtracting projection of that vector onto my previous two vectors, V1 and V2, right? So that's my projection of X3 onto V1 and V2, spanned by V1 and V2, right? And again, here, just compute your dot products, right? Those going to give you your constants, right? This dot product over dot product constant, kind of plug in the vectors you have, right? X3 you have. So yeah, and compute, right? Not that bad. I mean, you can rescale that one too, right? I don't like this 1/3. So I'll just multiply everything by 3 and get my V3 in a much nicer form. And so, yeah, and I'm getting my, by construction, this is going to be an orthogonal basis, right? And if I wanted to make it orthonormal, then I would just divide each one by its length to make them all equal, have length 1. That makes sense from last time. So then for your midterm 3, so there definitely will be a problem on your midterm 3, like when I'm giving you basically something exactly like this. I'm giving you like 3 vectors that form a basis for some subspace, and I'm asking you, well, use those vectors to construct an orthogonal basis or construct an orthonormal basis. So you just have to kind of follow this procedure to do it. It's very straightforward. Any questions? No? Okay. So and then the last part of that chapter we didn't finish last time. So I mean, we're not really using it too much, but it's kind of a very useful little trick that, I mean, if you guys do more linear algebra, especially if you start like writing some numerical algorithms to like solve linear systems, like this decomposition comes up quite a bit. So I thought we'll kind of run over it real quick since it's also related to our like orthonormal basis, right? But what our QR factorization theorem says that if A is, it doesn't have to be a square matrix, it's an m by n matrix with linearly independent columns, right? Then A can be factored into A equals to QR. So the product of two matrices, where Q is an m by n matrix with columns that form an orthonormal basis for column space of A, right? And R is an n by n upward triangular invertible matrix with positive entries on its diagonal. All right, so how does this all come together? It's actually not that hard, because if you look at your matrix A, right, we know that it has linearly independent columns, right? And it's an m by n, so it has n linearly independent columns, right? And those columns form a basis for the column space of A, right? The columns of A. But if I know the basis for column space of A, I can use my Gram-Schmidt process, right, that we just did, in order to construct an orthonormal basis out of the basis that I already have, right? So if my subspace W is column space of A, that's what I'm looking at, right? I constructed my orthonormal basis, and I can put those orthonormal bases as the columns in my matrix Q. So that's how, well, that's what my Q is going to be, right? It's just basically, I redid my bases from vectors x1 through xn with Gram-Schmidt to make them unit vectors that are orthogonal, u1, u2, un. And then to find what R is going to be, what you have to do, I mean, you can kind of go, we can do this here. Not so this was my original basis, right? The columns of A, right? So for each k from 1 to n, I could have n basis vectors I have to go through. if I'm looking at the span of those vectors x1 through xk, right, my kth column of A is going to belong to that span, right? Because I mean, it's right here. And if we're using Gram-Schmidt, I also know that this, for any k, the span of those vectors will be equal to the span of my new orthonormal vectors. So, but if xk belongs to the span of u1 through uk, I know I have weights, corresponding weights, and I'm going to label them like R1k, R2k, right? Because I have k going from 1 to n, right? So I'm just using k to specify that those are related to the kth column of A. Right, so because xk belongs to the span, that means there are some weights that I can assign to my basis vectors. And also because, for V, my vectors keep going to un, I'll just label them with zeros, right? Because xk belongs to the span of just those first k vectors. So, and like the part about things being positive, I mean, I can choose my rk to be equal to be greater than zero. Because I mean, if it's less than zero, I can just multiply my corresponding basis vectors by -1, right? Like I can make this, I can force this to be positive easily. So, but then if I rewrite this kind of in more like a matrix multiplication format, right? Those are my weights multiplied by basis vectors that I can imagine as columns in a matrix, multiplied by my coordinate vector, right, of xk relative to u, to use. Now, and again, if I rewrite this in even more in a matrix vector format, right, I mean, this is my matrix Q, basically. And those vectors, I'm going to call them vectors Rk, right? Because for each k, I can write a particular vector, right? And the number of zeros will change, right? If k was 1, then I'll just have one entry and things like that. So and that's how I would construct my matrix R. Like matrix R will just consist of those columns R1 through Rn, right? Because if I'm looking at my matrix A has columns x1, xk, xn, right? And each column xk is q times rk. So my columns x1 through xn are the same as q times r1 all the way to q times rn, right? Which basically is my qr, right? If I factor out q. That makes sense? I'm gonna do an example here. So that example we did earlier, with using the, so if I have this matrix A here, 1 0 0 1 1 0 1 1 1 1 1 1, right? So my columns of A are those three vectors, right? 1 1 1 1 0 1 1 1 and 0 0 1 1, right? So we worked with those earlier, right? So those guys form a basis for the column space of A, but they're not orthogonal, right? They're not an orthonormal basis. So we need to construct an orthonormal basis out of those guys. And we already did the work here, right? We used the Gram-Schmidt to construct the orthogonal basis, right? So we can rewrite this here. I guess I didn't rescale that one yet, but right. I mean, this is what we got from our Gram-Schmidt example earlier. So for QR factorization, when you construct your matrix Q, they don't just have to be orthogonal, they have to be orthonormal. So they also have to have length 1, right? But it's not hard to deal with. I mean, basically all you do is rescale them so that they have length 1, right? And rescaling them or normalizing them so they have length 1 means that you just divide it by its length, right? So and take a square, like it would be like sum of squares and square root. All right, so this one would be sum of squares of 4 square root 2. And the same here, you're basically dividing vectors by their length. And now they're going to be unit vectors. this doesn't change orthogonality, right? Because remember our relation, if I had like a constant multiplied by a vector and I'm dotting it with another vector, right? I can always like factor it out. If this equals to 0, I mean, constant doesn't affect it. My dot product equals to 0, right? So, okay, so I have my orthonormal basis, and this forms columns of my matrix Q. Not that bad. I mean, you just have to do some work converting columns of A into orthonormal columns that also span the column space of A. So my matrix Q, and then how do I find my matrix R? It's actually kind of, you don't have to do it. It's very straightforward way, kind of like we did in the proof. But I mean, there's a trick to it because if you know A and you already know Q, you should be able to find R, right? Also, you know, because Q is orthonormal, right? We know that QT, Q transpose times Q equals to I, right? So we showed that before. And what you can do in this formula, right? I have A equals to QR. You can just multiply on the left by Q transpose, right? Multiply both sides of this by the same matrix Q transpose. Because then Q times Q transpose is I times R is R. So I can basically compute R by doing Q transpose times A, right? Which is not hard, right? Much easier than finding inverses. I know what my Q is. So then to find Q transpose, right, my columns become my rows, right? Column becomes row, column becomes row. That's my Q transpose, my matrix A. You just have to do matrix multiplication, and row by column, and you're basically computing your matrix R. And you're done. Right, so I got my QR factorization, matrix A equals to Q times R. So my orthonormal columns and my kind of upper triangular matrix here. Right, so I have positive values here, and I have zeros here. So I have triangular matrix R. Again, we're not gonna use, yeah, we're not using this in our next chapter really, but I mean, this comes up a lot, like you guys do more like computational linear algebra, you'll see it again. So I thought maybe we should kind of do this since it was in your chapter. That's pretty much the last thing for the check, I think, for midterm 3. Any questions on the QR factorization or inner product stuff?
Not for me, Professor. Thank you.
Everything okay? All right, so all the inner product things are pretty fresh, but I think so. I was grading your guys' quizzes 9. I mean, I thought you did good, but I think like your quiz scores started deteriorating a little bit towards the end. So we'll kind of we'll review chapter 5, and then I'll go over the quiz solutions for what we had with chapter 5. So it's like quiz 9. I think there's actually a lot of you did some mistakes there, and I mean there will be questions on the midterm that are very similar to your quiz 9 problems, and so I want to really be good at doing those types of problems. So chapter 5 dealt with eigenvalues, eigenvectors, like diagonalization, things like that. But mostly it's eigenvalues and eigenvectors. So what were eigenvalues and eigenvectors? I mean, those are those special kind of vectors and associated values where basically, if you look at it, the action of the matrix on the vector x is equivalent to just scaling that vector x by some constant value, right? So matrix multiplication is equivalent to multiplication by a constant. I mean, that's what was special about those kind of eigenvalue, eigenvector pair. And the other important part about eigenvectors too, I really need to have a non-zero vector. So I mean, if x is 0, this is 0 equals to 0. There's nothing interesting there. So I'm really looking for a non-zero vector x that basically scales by lambda by an action of the matrix A. All right. So and such lambda would be my eigenvalue, and such vector would be my eigenvector. So in other words, if you put it into kind of like our terminology and things we did in the class, since x is a non-zero vector, right? If I put everything on one side, set it to 0, right? So ax minus lambda x and factor out x. So that would be a minus lambda I times x. So my eigenvector is basically a non-trivial solution of this homogeneous system, right? Where now it's not my matrix A, it's the matrix A minus lambda I, right? So A minus lambda I times x equals to 0, and x is a non-trivial solution. And so from that, we can get a few things, right? We can basically get both eigenvalues and eigenvectors, but you get eigenvalues first, right? Because if I'm looking for non-trivial solution of this, remember about our invertible matrix theorem when we did that, this guy will have a non-trivial solution only if this matrix A minus lambda I is singular, right? If this matrix was invertible, then I'm just multiplying by inverse on both sides, and I'm getting unique solution x equals to 0, right? So I really need to have this matrix being singular in order to get a non-trivial solution, right? And we know when we did determinants that if the matrix is singular, then the determinant of that matrix equals to 0. So that gave us our characteristic equation that we use to find our eigenvalues lambda, right? So if you compute the determinant, it's going to be a scalar quantity, right, with some unknown lambdas. So I'm getting a polynomial in lambda, which I can solve for my eigenvalues lambda. All right, but again, it came from the condition that the matrix has to be singular so that I can find a non-trivial solution that's an eigenvector. But you always find eigenvalues first, and once you find eigenvalues, you basically can start looking for your eigenvectors. And when you look for eigenvectors, you basically have to look for, well, what are those non-trivial solutions? And the non-trivial solutions of the system we know are basically a null space of the matrix A minus lambda I. So we can look for basically a null space of this, right? And this should not be equal. And those are my eigenvectors. I mean, null space will include 0. All right. So, I mean, yes, you will have to solve the system, and just like when you're looking for null space, you'll find like x equals to constant vector, things like that. All right, so that's kind of the basic setup of this. And I mean, there are some little shortcuts, like if you're looking for eigenvalues, we can look at the matrix. If the matrix is triangular, and we'll do some example. I mean, triangular means I have all zeros in like an upper or lower triangular region. So not on the diagonal, but kind of upper triangular region, the lower triangular region. That'll be a triangular matrix. And if you have a triangular matrix, we showed that all of the values on the diagonal are going to be my eigenvalues. So for triangular matrices, you don't have to do the determinant, right? You can just pull your eigenvalues directly from the diagonal, but only if you have kind of zeros in lower or upper triangular regions. So and then we also did there was a few theorems that kind of give us some shortcuts, right? Because ultimately we'll be looking for like bases, eigenvector bases for subspaces and things like that. And I kind of started with noting that if I have distinct eigenvalues, so if I find eigenvalues for my matrix, they're all different numbers, none of them are repeated, then each one of those eigenvalues, I mean, it will have at least one eigenvector, right? I mean, depending on multiplicity, but if I have multiplicity 1, they will all have, each one will have one eigenvector. I mean, just by definition, because if I'm looking for eigenvalue here, I'm assuming that I have an eigenvector. All right. Those will be linearly independent. And so for distinct eigenvalues, eigenvectors will be linearly independent. We showed that before. And when I'm computing my eigenvalues, again, I'm getting my characteristic equation, right? When I'm doing my determinants, setting it equal to 0, right? And I mean, from this meme is constant matrix. So I basically have entries that are either constant or constants minus lambda. When I'm multiplying everything using my determinant or cofactor expansion for determinant, I will end up, after simplification, with basically some polynomial, which I can factor. I mean, hopefully easily. I mean, sometimes it's a little bit harder, but you know, we're not dealing with very like high order problems. So usually it's fairly simple to factor those polynomials. And we know at least if we're not dealing with complex eigenvalues, if all of my eigenvalues are real, right? Remember all those theorems from algebra, right? I am going to add up to n with all of my multiplicities of lambda, right? The dimension a by n, right? And I can factor everything into linear factors. I mean, unless I have some complex eigenvalues. Right? So we'll talk about complex in a second. All right, and I'll get my n eigenvalues, and you should always note the multiplicities of them, because when we start finding eigenvectors and trying to diagonalize matrices, this will become important. All right. So we also had a theorem that said that, well, if I do have some eigenvalues that are repeated, so maybe I have like 3 eigenvalues, lambda 1 equals to 3. So I have lambda minus 3 multiplicity 3. What we know is that the dimension of the eigenspace for a particular eigenvalue is always going to be less than or equal to the multiplicity. So like if my multiplicity is 3, I can have 1 eigenvector, 2 eigenvectors, or 3 eigenvectors. Or dimension of my null space could be 1, 2, or 3. And for diagonalization, remember, we really need to have full. If I have like multiplicity 3, my dimension of the null space should also be 3. Right, so I can kind of generate the eigenvector basis for Rn. All right, but those are kind of like basic facts about, you know, what do we get from our characteristic equation. I mean, like the very last chapter we did was with complex eigenvalues. So, I mean, this is a polynomial, right? And we know from algebra for polynomials, I mean, I can factor out any polynomial with real coefficients and two linear factors, but sometimes I'm going to end up having some complex eigenvalues there. All right, but if my A has all real entries in it, and I do have complex eigenvalues, what I will end up with is that, well, one, my complex eigenvalues will come from complex conjugate pairs, because if I did have real coefficients here, my complex roots for the polynomial will come from those irreducible quadratic factors, right, which would have complex conjugate roots. So, and not only that, like if I know I have one complex eigenvalue like lambda 1 plus I know that I will also have another eigenvalue 1 minus I, like its complex conjugate. And not only that, I know that my eigenvectors corresponding to those eigenvalues are also going to be complex conjugates. So it's actually like a little bit easier to deal with those, because like if you find an eigenvector for your first complex eigenvalue, for your second complex conjugate eigenvalue, you don't really have to compute anything anymore. You just take the conjugate of the first eigenvector. And we'll do example. Just kind of running through all the theorems first. Yeah. Then with all of that, we kind of went to diagonalization of matrices, right? Because it's easy to deal with matrices that are diagonal, right? Diagonal matrices just have non-zero entries on the diagonal and non-zero everything everywhere else, right? I can kind of bring those matrices to different powers very easily. It's just a lot easier to deal with those. So and we know that if A is diagonalizable, that means that A is similar to some diagonal matrix D. Right, and the problem is just I need to find a matrix P so that P times D times P inverse, gives me A. Right, but for that, I mean, basically what we have to do is find an eigenvector basis for Rn. Right, so for each one of those eigenvalues, I'm finding my eigenvectors, and I can put those eigenvectors in my matrix P. Right, and then my matrix would be diagonalizable, but I do need to have all of the eigenvectors, right? So depending on multiplicity of eigenvalue, right, I really need to have the same number of eigenvectors as the multiplicity of that eigenvalue in order to be able to diagonalize the matrix. So like if I have eigenvalue of multiplicity 2, and I'm solving for eigenvector and I'm only getting one eigenvector, not two, I can't diagonalize that matrix, right? But if dimensions of each of the eigenspace for each one of the eigenvalues equals to the corresponding multiplicity of the eigenvalue, then I'm good. I have enough vectors to form my P, and I know by construction that my P times D times P inverse, which you also have to find, is going to be equal to my A. Right? So it's kind of like decomposition of A into matrix of eigenvector basis, diagonal matrix with eigenvalues and a diagonal and an inverse of P. Let's do, that was your first problem on the quiz 9. So that one was, yeah, I probably should have made the quiz a little bit shorter. And that one was a little bit long, but I mean, not too crazy long. So what we have to do here, so I have a matrix 3 by 3, and I want to find eigenvalues and eigenvectors for this matrix. That was the first part. So, I mean, you always start with looking for eigenvalues first, right? Because you're using your characteristic equation, right? I know that determinant of A minus lambda I should be equal to 0. So, okay, I'm just writing down my A minus lambda I. I'm basically subtracting lambda from everywhere in the diagonal. The rest is the same. And I'm taking determinant of that. So that one is 3 by 3. And unfortunately, there is no like columns with mostly zeros. There's no zeros at all. So just pick any row or column you want and expand along it. So I'm expanding along the first column, all right? But remember, when you're doing your cofactor expansion, I mean, you take in the value here, you multiply it by what's left when you delete its row and column, but you also have to take care of the signs, right? You always have this like checkerboard pattern, like plus, minus, plus, minus, plus, plus, minus, plus, minus. All right, so don't forget your signs in cofactor expansion. So for this guy, I have plus 7 plus lambda times the determinant of what's left when I delete row and column. So kind of this section here. Then the next one, I have 2, but this is plus minus, so I have to put minus 2 times determinant of what's left when I delete row and column. So 416 minus 2 minus 5 minus lambda. All right. And then the last one, I have plus and minus 2. All right, and then determinant of what's left, right, when I'm deleting row and column with minus 2. All right, and now we have just kind of two by two determinants. All right, so positive, negative, diagonal, positive, negative, positive, negative. So this would be this times that minus this times this. All right, so I have my 5 minus lambda times minus 5 minus lambda. And then this is a negative diagonal. So I saw a lot of you forgetting to put minus. This would be minus 8 times minus 2. This will become plus. You can do the same for those two guys also. Right. So, and I mean, yeah, it gets tedious a little bit, but basically just expand everything and then try to kind of factor everything back. Well, expand everything and then try to like factor everything. I mean, usually it shouldn't be too bad. Here it wasn't too bad. So here you can factor it into lambda minus 3 and lambda minus 1. So Remember, this is our characteristic equation, so we have to set this equal to 0 because our condition determinant of this matrix equals to 0, so that this matrix is singular, so that the equation A minus lambda I times X equals to 0 has a non-trivial solution. All right, but from this we're getting, okay, I have one eigenvalue is 3 of multiplicity 2, right? It's repeated twice. And I have another lambda of multiplicity 1, right? Lambda equals to 1. It just repeated once. So overall, I have 3 by 3 matrix. I have 3 eigenvalues, right? It's just one of them is repeated twice. Once you get eigenvalues, you go and compute your eigenvectors. So I'm just gonna do it one at a time. So for lambda 1 equals to 3, when I'm looking for eigenvectors, I'm really looking what is the null space of A minus lambda I, my lambda equals to 3. So what is the null space of A minus 3I? So write down your matrix A minus 3I. I'm just taking my A and subtracting 3 from the diagonal. Like simplify, and I'm getting this matrix here. I mean, I already see that, I have very linearly dependent rows, right? I mean, if I just divide this by 4, this by 2, and this by minus 2, right? I mean, all of those rows are basically 1, 1, and 4, right? So this is row equivalent to 1, 1, 4, and then 2 rows of zeros, right? And so from here, again, we can get our null space. Only have one pivot position. So x1 is expressed in terms of x2 and x3. So I can say, okay, well, x2 is alpha, real number, x3 is beta, real number. And then x1 is minus x2 minus 4x3. Right, because I'm solving homogeneous system. Right? So basically I have like zeros here that I'm not writing. All right, so x2 is alpha, x3 is beta. So x1 is minus alpha minus 4 beta. Put it in your vector, right? So this is the vector, the general solution of the homogeneous system. I have two constants, arbitrary constants, alpha and beta. So I'm splitting this into two vectors, one multiplied by alpha, one multiplied by beta, right? Alpha is real number and beta is real number. So I have like 2 degrees of freedom, you can think of it. And I have two vectors basically spanning my eigenspace of lambda 1 equals to 3. And those are going to be my eigenvectors. So I have lambda 1 equals to 3, multiplicity 2. And I'm getting 2 eigenvectors in my eigenspace, which is nice because my other lambda is multiplicity 1. So I know it will have one eigenvector. I mean, this is the only one that would have caused me trouble when I want to diagonalize the matrix, because sometimes it may not have both eigenvectors when you have one. I mean, here it has 2, so I mean, I already know my matrix will be diagonalizable. So I will just have to find my second or my third eigenvector corresponding to my lambda 2, right, equals to 1. But it's same, doing it the same way, right? So you're basically looking at what is the null space of A minus lambda I, my lambda equals to 1. All right. So yeah, just compute your A minus 1 on the diagonal. All right, simplify. And then I mean, you can do again like row reduction to bring it to some row echelon form where you can see where your pivots are. All right, so here I have 2 pivots and I have 3 variable at my x3. All right, so I'm gonna say x3 is alpha, some real number, then x2 plus x3 is 0, so x2 equals to minus x3, and then x1 equals to minus x2 minus 4x3. Right? So I'm expressing basic variables x1 and x2 in terms of free variable x3. Right? So when you're getting, again, everything in terms of alpha, which is my x3, I put it in my vector x, so that's my non-trivial solution to a minus 1i x equals 0. I have 1 degree of freedom, alpha belongs to real numbers. And I can pull out my third eigenvector from here, right? -2, -1, 1. So I have my second lambda of multiplicity 1 has one eigenvector, -2, -1, 1. That's my eigenvector. And my eigenspace has dimension 1 because it's a span of just that one vector. All right. So eigenspace of dimension 1 equals multiplicity 1. And then here in the previous one, I had lambda 3 multiplicity 2. My eigenspace is spanned by two vectors, so it has dimension 2 equals to multiplicity. So since multiplicities of my eigenspaces equal to, well, since dimensions of my eigenspaces equal to multiplicities of corresponding eigenvalues, I have that my matrix is going to be diagonalizable. So I can diagonalize it. And when I'm diagonalizing it, I am basically constructing my matrix P by putting my eigenvectors as columns. Right? So columns are eigenvectors. So this is V1, V2, and V3. Now, and I mean, it doesn't really, I mean, you want to kind of put together the ones that relate to one eigenvalue, but I mean, you don't have to, right? You could have put in like lambda 1 first, right? But I mean, what matters is depending on how, in which order you put those eigenvectors in P, this is going to be the order of the eigenvalues in a diagonal here, right? So like if you put -2, -1, 1 first, and then -4, 0, 1, -1, 1, 0. If that was your P, then your corresponding D is going to be 1, 0, 0, 0, 3, 0, 0, 0, 3. All right, so kind of like the placement of eigenvectors here will give you the placement of eigenvalues on the diagonal. That makes sense? All right, so I mean, basically it's, oh, you're almost there, right? Because if you know P, you know D. I mean, the only other thing you might need to know if you're trying to use this for computation, you need to find P inverse. So I mean, that's kind of like the annoying tedious part where you do have to do your row elimination algorithm, right? Just like we did before, you put your P that you know, you put your identity matrix here, and then you do your row elimination until this becomes identity and this becomes P inverse, right? So if you did that, I'm getting P inverse equals to that. All right. So we're basically done, right? We got our decomposition. This was our matrix A. We got P that we constructed out of eigenvectors. We have D with eigenvalues on a diagonal. And we have P inverse that we basically got by taking an inverse of P. And so we have kind of this decomposition into product of three matrices for my matrix A. So and how can we use this? And that was like the last section of that problem. I was asking you to compute the 10th power of A. Now, so, I mean, yeah, you can take your matrix A and multiply it by itself 10 times, but that's just going to be a lot of work doing it by hand. I wouldn't do it. But if I know my decomposition for A, PDP inverse to the power 10, you think about if I write all of this factors out, I mean, it's basically PDP inverse 10 times, right? But if I put them all one by one, this P inverse times P is going to be equal to I. This P inverse with the next P is going to be equal to I. P inverse here with this P is I. Right, so all of those pairs, P inverse times P, will cancel. Right, so all I will have left is just the first P, then D, I, D, I, D, I. So it's just P times D to the power 10, and then only the P inverse survives here. So basically, bringing A to the power 10 is the same as bringing my diagonal matrix for A to the power 10, but then I just have to kind of multiply it by P inverse on both sides. But bringing diagonal matrix to the power 10 is a lot easier. You're just basically bringing everything on a diagonal to the power 10. So my a to the power 10, 3 to the 10, 3 to the 10, 1 to the 10, all right? And I already have my p and my p inverse. And this is my t to the power 10. So I mean, I still have to compute a little bit, but I mean, it's basically done, right? You can compute 3 to the power 10 and then just do matrix multiplication. That makes sense? You guys have any questions on this? That was from your quiz problem. I think a lot of you just skip this part, but when you have problems on the exam, especially like multiple part problems, like the last part, I mean, usually the last part kind of uses everything you do in the previous few parts. So since you had to get the PDP inverse factorization for A, that means you know, the last part, when I'm trying to find a to the power 10, I mean, you should be able to use this somehow to make it easier. Right, so again, you can expect something like that again on your midterms. I'll just make it like a 20-point problem or something, because it's a little longer and do a few steps. Any questions, guys, on this? You know, good. All right. So I had the second problem on quiz 9. Again, I think more of you did this good, but still, I don't have a feel like most of you are kind of getting the full picture. So you should do this again. So here I'm coming for one. Like, so I'm given the matrix again A, right? And I want to find eigenvalues and eigenvectors. So a lot of you did the characteristic equation again. And I mean, you can do that. Nothing wrong. Like you get the right solution, but this is one of the examples where you can use a little shortcut, right? If you notice, I mean, this is going to be a triangular matrix, right? I have values on the diagonal, and then I have all zeros in the upper triangular region. All right, so this is a triangular matrix. And for triangular matrix, my eigenvalues are values on the diagonal. So you don't have to, spend time doing characteristic equation. You can literally just pull out the values from the diagonal. So I have lambda equals to 4 with multiplicity 2, and lambda equals to 5 with multiplicity 1. Kind of similar like before. I have like one eigenvalue multiplicity 2, one multiplicity 1. So when you start doing your eigenvectors, again, you just write down your A minus lambda I for lambda 4 and lambda 5. So for lambda 4, you do A minus 4I. You can just simplify and bring it to row echelon form. I mean, here it looks like I have 2 pivots in a 3 by 3 matrix. So I only have one free variable, x2 equals to alpha. If I have one free variable, I'm going to have only one eigenvector spanning the eigenspace for that. So because I have multiplicity 2 here, and I only have one eigenvector, so my dimension of null space of A minus 4I is just 1. All right, but multiplicity 2. I'm not going to have enough eigenvectors to be able to diagonalize A. All right, so 1 is not equal to 2. So I already know my A is not diagonalizable. I don't have enough eigenvectors. But I mean, I can still find the other one, right? So for lambda 5, you can just plug it into A minus 5I. Simplify. Again, you can look at your 2 pivots. My free variable is x3, and expressed in terms of x3. So I'm getting 2 eigenvectors, right? One for 4 and one for 5. Got eigenvalues, got eigenvectors, but A is not diagonalizable because I only have one eigenvector for eigenvalue with multiplicity 2. And I don't have enough eigenvectors to form an eigenvector basis for Rn. Yeah, I can say like not enough eigenvectors for basis for Rn. All right, so it's not diagonalizable. That makes sense? If you have questions? No. Moving on. So complex eigenvalues. I don't think you don't have a quiz problem for that yet. All right, so for complex eigenvalues, I mean, if you have a question, it's going to be something like this. I'm going to test. All right, so I don't know, your book didn't go too far into complex eigenvalues, but if you guys take like differential equations class later, I mean, this will come up again, and you'll kind of relearn all of this again, and you'll learn how to like, deal with those complex eigenvectors a little bit better too. But, we should do at least a little bit of it so you're kind of familiar with the fact that, I mean, yeah, sometimes you do have complex eigenvalues and complex eigenvectors, and I mean, that is okay. So you do it pretty much the same way, right? I have a matrix. I mean, I don't even know if I have complex eigenvalues and eigenvectors yet, right? I just have matrix and I want to find eigenvalues and eigenvectors. I do my characteristic equation, right? Determinant of A minus lambda I, again, just subtracting lambda from the diagonal. I have -2 -5, right? Then, I mean, that one is easy. Again, just do your diagonals, positive, negative. So 1 minus lambda times 3 minus lambda minus 5 times -2. Right, expand everything, right? Because you're going to want to try and factor this. And if I look at this quadratic, I try factor it, I can't really find anything, right? I mean, what's the product? Like A times B such that -4 is A plus B, right? A plus B minus 4, AB equals to 13. I can't find anything. So I can't factor. But that's okay because it's quadratic. And for quadratic, we have our quadratic formula. And so I have my kind of minus b coefficient plus minus b squared minus 4ac divided by 2a. You guys all know quadratic formula. So just use quadratic formula for solving this for roots lambda. And yeah, once you start doing it, it makes sense why you couldn't really factor this, because you do end up having complex roots here, right? And my square root here, I have a negative number. So square root of -36 is going to be square root of 36 times square root of -1, which is I. And so I have 4 plus -6i. And simplify. So those are my complex eigenvalues. All right, 2 plus -3i. And again, so, I mean, I already know I have complex eigenvalues that come in complex conjugate pairs, right? Because my polynomial has the real coefficients. What you do with eigenvectors, they will come in complex conjugate pairs, but you start with one of the eigenvalues. Just pick one, like positive or negative, it doesn't matter. So I'm picking like lambda is 2 plus 3i. Now, do the same thing. I'm looking for null space of a minus lambda I. So except my lambda now is complex number. So taking my a, I'm subtracting my lambda from diagonals. Like I simplify a little bit, so I get this. And then the thing is here that, I mean, I could try and like bring it to a row echelon form, but I really don't need to, because I already know, well, if I have this eigenvalue, I will have one eigenvector, right? And for this 2 by 2 matrix, I mean, what are my options? If I have one eigenvector, I will have one free variable. I'm not going to have two eigenvectors, right? Because it's eigenvalue of multiplicity 1. So, I mean, I know that my two rows have to be linearly dependent. All right, so I don't really need to do, I can just pick any one of the rows. I can pick the first row of the second row. So you just pick the first row and use this to get your relationship for your eigenvector. All right, so pick the first row I have -1 minus 3i times x1 plus 5 times x2 equals to 0. And here I just solve for x2. Right. I have 1 plus 3i x1, so I can put this in my vector. And I can rescale it to make it look nicer, right? I can multiply by 5. So I have 5 and 1 plus 3i. Right. So there's nothing wrong with doing that. And another thing is if you pick a different row, I mean, I feel like doing some example problems and your answer doesn't match solutions. Right, if I picked a different row, so if I pick the second row, then my relationship would be like -2x1, right, plus 1 minus 3i x2 equals to 0. So I can solve for x1. Right, x1 is 1 minus 3i divided by 2 x2. So my eigenvector here would be x equals to x2 is free variable, and x1 is 1 minus 3i over 2 and 1. And I can also rescale it, like multiply by 2. So I would have 1 minus 3i and 2. All right, so this is the eigenvector I got from using the first row, and this is the one I got from using the second row. But they are actually the same vector, because remember, now we're dealing with complex numbers. So when I'm doing this rescaling here, right, I multiply it by 2 to rescale it to get rid of the denominator. I also can rescale it by multiplying by complex numbers, right? So here I can use a constant to rescale if I use a complex conjugate of 1 minus 3i or 1 plus 3i. So I'm just multiplying both. I'm rescaling it, right? I will end up with my multiplication of complex conjugates. I will have 1 plus 3 squared, 1 plus 9. And on the bottom, I'm going to have, I'll rescale it into 1 plus 9, and then 2 times 1 plus 3i. All right. All right, just rescale it using complex numbers. So I will have 10 into 1 plus 3i. And if I divide by 2, I'm going to have 5 and 1 plus 3i. All right, that was eigenvector I'm getting from second row. But that's the same eigenvector I have here, right? So kind of getting it from first row, second row, you're getting the same vector. It's just, it might not look to you as the same vector because you have to keep in mind that when you're doing rescaling, you basically can multiply this vector by scalar, and by scalars now we mean it could be any complex number. All right. So I kind of like up to rescaling complex numbers. So all right, but I mean you got your one eigenvalue, you got your one eigenvector. So do I want to do the same thing for the second eigenvalue? I mean, I can, but I really don't have to, because if I look at kind of what I have for my kind of pairs of complex eigenvalues, eigenvectors, but if my matrix A has real entries, right? So there's no complex numbers in my matrix A. Then kind of like complex conjugate of A equals to A itself. So if I look at my pair, right, AX equals to lambda X. So this is lambda X or my eigenvalue, eigenvector pair. If I take conjugates of both sides, right, complex conjugates, then our conjugate of AX is conjugate of A, conjugate of X, conjugate of lambda X is conjugate lambda, conjugate X. And conjugate of A is A because A is real. But then what we end up with is that A times conjugate of X equals the conjugate lambda conjugate of X. But this is exactly the definition of eigenvalue eigenvector pair. So my complex conjugate lambda corresponds to an eigenvector that's just the complex conjugate of the eigenvector that corresponded to lambda, right? So lambda X eigenvalue eigenvector, then their conjugates are another eigenvalue eigenvector pair. So because we already found lambda 1, 2 plus 3i, and its corresponding eigenvector, Then to get the second one, just conjugate, right? My lambda 2 is lambda 1 conjugate. And then my V2 is going to be V1 conjugate. So you don't have to do it the second time. Yeah, that makes sense. Yeah. So if you guys take like differential equations class after this, like you will deal with a little bit of this, and there'll be like a ways to like kind of like split up and convert your eigenvectors to real eigenvectors. But I mean, you can just kind of get it there. I think for now it's kind of keep in mind that you can get complex eigenvalues and complex eigenvectors. And just know how to solve a problem like this. That's kind of a good example of a problem you can have for next stuff on the test. Any questions? No. Well, I have a little bit left here. Finish that part. So the kind of like the last, well, I guess the last part was complex eigenvalues, but we also skipped the part in the eigenvectors, eigenvalues chapter where we looked at all of this from a point of view of linear transformations on vector spaces. So, I mean, not all linear transformations would be defined as matrices, but if you have finite dimensional vector spaces, I mean, it's easy to, well, not necessarily easy, but you can represent, you can have a correspondence between that linear transformation and a matrix multiplication, right? But to kind of redefine all of this eigenvector eigenvalue pair in terms of general linear transformations, because that could also work for infinite dimensional vector spaces. Like you can have like a space of all polynomials or something and look for eigenvectors, eigenvalues. So for general linear transformations, it's similar setup, right? Like applying transformation T to X results in just rescaling of X by an eigenvalue lambda, right? And your eigenvector would be a non-zero vector that kind of satisfies all of this. And then we basically went to, again, back to trying to rewrite everything in terms of kind of matrices and vectors in Rn, right? If I have a basis for my vector space V, I'm kind of derive the formulas for like matrix representation for transformation T relative to beta, right? And kind of to remember this better, you can kind of go from the start, right? What I would do if X is in V and those B's are my basis for V, then I can express X as a linear combination of those basis vectors. So my coordinate vector beta of X is just those weights R1 through Rn. Then if I take linear transformation of my vector X, right? But it's linear, so when I'm applying it to the sum multiplied by constants, I can split this up and factor out the constants. So by linearity, my T of X would be this. And then if I'm taking beta coordinate transformation of T of X, right? The beta coordinate transformation is also linear. So again, when I'm applying it to that whole thing, I can factor out the constants and split it into this big sum. Right? And from here, again, I have weights multiplied by those column vectors. So I can rewrite it as a matrix multiplied by a vector that consists of my coordinates. Right? So that's how we got basically this representation here, right? So kind of like instead of looking at, what happens to, right? I'm taking X and transformation takes X to T of X, right? Here I'm looking what happens to my coordinate vectors, right? X and coordinate vector of T of X when I'm applying T. And so I'm basically switching this to looking at what happens to X when I'm multiplying X by some matrix A that's equivalent to action of that linear operator. And that matrix A is my T of B. So it's matrix representation for my linear transformation relative to the basis beta. All right, so I could have computed this way. All right, the columns are basically beta coordinate vectors of transformation of all of my basis vectors. All right, so that's useful formula. All right, and now we did some examples for this. Those are kind of good problems for the test. All right, so say if I'm given a linear transformation, like from space of polynomials of degree at most 2 to itself. And my transformation is given to me by, well, if I take any general polynomial, what I'm going to get is a1 coefficient of t to a2 times t. So if you guys did calculus, I mean, this is just your differential operator. I'm differentiating that polynomial of degree 2. All right, so it is a linear transformation. And notice it's not defined in terms of the matrix here. It's just defined in terms of what this t does to a polynomial, right? It removes the constant term. It divides t term by t, and then it's kind of multiplies t squared term by 2 and reduces power of t by 1. That's how that linear transformation is defined. And if I look at the basis for P2, my standard base is 1t squared. Right, if I want to kind of rewrite this whole thing in terms of matrix multiplication, like I don't want to deal with polynomials, I'm comfortable working in like Rn. Right, so I want to rewrite everything in terms of Rn vectors. So to construct my matrix T, right, I mean, I can rewrite this as a coordinate vector. I can rewrite my x as a coordinate vector. Right, my p of t in terms of beta is just my coefficients. And my coordinate vector of t of p is, right, constant a1, coefficient of t squared missing. So I know coordinate vectors of those times. So what is the matrix? Just use the formula, right? So evaluate your transformation at all of the basis vectors, right? T of 1, 0, right? Because if I have 1 here, everything's 0, so it'd be 0. T of t1, t of t squared, 2t. And then get coordinate transformations of those. And those are basically your columns in your matrix T beta. And so you're basically rewriting this definition of a transformation in terms of kind of your 3 by 3 matrix and R3 vectors. That makes sense? All right, so kind of know how to go in between kind of like this definition to definition in terms of like matrices, right? So kind of know how to construct this matrix for linear transformation with respect to basis beta. I think just enough time. Right, so kind of like the last thing we did is kind of connecting all of this to diagonalizability and things like that. But so basically when you have your linear operator, and suppose I can define it in terms of matrix A, all right? And I have a basis for my vector space V. So I can choose different bases for my vector space V. And depending on the choice of those bases, I mean, that matrix is going to be, my representation of T relative to beta is going to be different, obviously. But what we can get from this is, I mean, given any basis for V, it doesn't have to be an eigenvector basis, right? I mean, we know from the formula for beta representation for T, that the columns are kind of beta vectors of T of B1 beta vector, like all the way to T of Bn beta vector. If I know that my T can be represented by a matrix, I can basically use T of Bk equals to ABk, right? Action of T is the same as multiplication by a matrix. And then next, what I can do is I can replace the transformation, kind of taking the beta coordinates by multiplication by P inverse, right? Where P is kind of a matrix constructed with my basis vectors. And I mean, that came from that coordinate transformation. My X was equal to P times X beta. Right? So X beta is P inverse times X. So like that P inverse multiplication basically undoes my coordinate vector and takes you back to X. So that's what you're doing here. Then just factor this out. You basically end up having your beta representation of linear transformation T is P inverse AP. Right? But remember when we did our diagonalization, right? For diagonalization, A equals to P D P inverse if P consists of eigenvectors. Right? And D is diagonal with eigenvalues on a diagonal. So, I mean, basically what we're getting here is that my T beta is what goes over here, provided that P consists of eigenvectors. Right? I mean, T beta is more general, right? It's not, it doesn't have to be diagonal. I can pick any basis and it's not going to be a diagonal matrix. But if my basis consists of eigenvectors, then my T of beta will be diagonal. Does that make sense? Right, so then that only have time for that. I just have time for that last problem. So that was the last problem on quiz 3. Right, so I was given, okay, I have linear transformation from R2 to R2 defined by this matrix A, right? And I want to find the beta coordinate representation for T so that, or I want to find the basis so that it's diagonal. And it's basically the problem of finding eigenvectors, right? You construct a matrix P based, construct a matrix P with columns that are eigenvectors. And I mean, everything just follows. It's just the problem again of finding eigenvalues, finding eigenvectors. And if you're using the basis of eigenvectors, then your T beta is going to be diagonal, right? So that was the problem here. And like, you don't have to find P inverse here, because if someone is just asking you the basis that will make T beta diagonal, just find eigenvectors and that would be your basis. All right. I think that for the, yeah, so for the section of eigenvalues, eigenvectors, I think we pretty much covered everything. Since we did like chapter 5 and chapter 6, so you'll have, well, I mean, half the problems are going to be from chapter 5 and half the problems will be on chapter 6. So I think so we reviewed everything from chapter 5 today. So guys, like look over your quizzes. I mean, I guess it's just quiz 9 and quiz 10 is still due. Yeah, so like next time we'll kind of go over some problems from chapter 6 to review more for the midterm, and then we'll do one more section on inner product spaces. So it's not very long. So we'll have time to kind of do that and like review more for the midterm. I mean, that's kind of the plan we have for now. And then next week we're not doing anything new. We're just going to kind of solve more problems and do review. Yeah, for the final. Any questions?
No, I just want to know if you're able to post the entire midterm 3 review, even though we haven't gone through it all completely.
Yeah, I can do that today.
Yeah, that would be amazing. I would like to prepare as and do it this weekend.
Yeah, I'll post the notes that I have like for the lecture, and then I'll post like the second part for the review for the chapter 6. Yeah, no problem.
Awesome, thank you.
Thank you, Professor.
All right, guys, I'll see you next time.
Bye, Professor. Have a good afternoon, and I'll see you Wednesday.
Hey, you too.
Actually, do you actually teach physically at Palomar College at all?
I mean, sometimes I do, yeah. I'm not sure though, like next semester what's gonna happen. Like they didn't really tell me. I mean, they just kind of like every semester they offer me classes. Sometimes it's online, sometimes it's in Palomar.
Okay. Do you teach other levels of mathematics like calculus 3 to diffie-qs, or is it primarily like linear algebra?
Oh no, I usually just take like yeah calculus and like differential equations. It was actually the first time they gave me the linear algebra. Um,
Well, I will say this has probably been the best linear algebra class that I've ever taken. I've taken one already.
oh really? Well, thank you.
Your the notes you provide us and the explanations are 1,000% better than most professors.
Oh, thank you. That feels good. Thanks.
It's proving in, I'm guessing, most of our grades. We're all doing, I'm guessing, well, if we're still here at this point.
Yeah, well, I mean, I think for online classes it's a little easier. But yeah, I mean, so I'm not going to like curve down like if you're worried about that.
No, I'm not concerned about that. I mean, I have everything I need to prepare for the test. You're not, there's no missing information, so thank you very much.
Yeah, no problem. Well, I mean, if you just kind of study and do your work, I mean, you shouldn't have to spend time like looking for information that, you know, I mean, I
Yeah.
guess you guys have other classes to study for. Like,
Yeah, I got all my engineering courses to take care of at the same time.
like good to have some classes, like, what I need. No.
Yeah, I will say that like nodal analysis and statics are definitely a handful with this class.
Yeah, I remember those. Yeah,
Yes, thank you very much, Professor. I
yeah,
definitely
no,
will write
yeah,
a
no,
good review on Rate My Professor.
no, thank you. Thanks. Well, I'll see you next time.
Thank you. Have a good afternoon. Take care.
So.